And it's Brian Day from NASA. I'm not sure if it's NASA Ames or
Ames, yes.
NASA Ames. And Brian got his first degree in psychology and then went on to get another degree in information systems, and not satisfied, went on with that to get another degree in astronomy. I know Brian's name a few years ago because he was a very popular speaker talking about the moon missions, not only the Apollo era missions, but the later missions, and he was a coordinator for that, and the public outreach message from NASA. And he continues to do that public outreach work today, as well as being very active in the Bay Area. Some of you may have even attended some of his talks in the local Bay Area. He's also a former chairman of the Lick Observatory, and he works with, or is associated with, NASA's SSERVI, which stands for Solar System Exploration Research Virtual Institute. So without further ado, I'm going to hand you over to Brian Day of NASA.
Thank you very much. Thank you, and thank you all for coming up here this evening. What I'm going to do is I'm going to give you a brief tour of the solar system, consisting of data that we have gathered from many different instruments aboard many different spacecraft across the solar system. And I'm going to use a tool that we call NASA's Solar System Treks. It's a tool that my team at NASA has developed. We use it for planetary science. We use it for mission planning. And we've also made a version of it available to the general public. So the kind of tour I give you tonight is something that you will be able to do from home because it's all web-based. You just point your browser to the address I'm going to give you, and you will be able to explore the many wonders of the solar system. We're just going to touch on a few of them tonight. So again, we're using NASA's Solar System Treks with a gathering number of portals for a growing number of worlds. We'll start out with the moon, and like any good GIS system, you can pan, you can zoom. We'll zoom in here to the crater Tycho, and one of the first things you might want to know is, well, how big is that? That's a very simple thing to determine. You just draw a line to measure diameter. So here we'll measure the diameter of Tycho crater, and we can see that it is in fact 84 point something kilometers. That's a big hole in the ground. The next thing you might want to know is, well, how deep is it? And again, as simple as drawing a line. This time we'll extend the line on either side a bit so we can capture the rim. And you can see that we actually can now generate an elevation profile, so you can measure the heights of mountains, the depths of valleys. You can do all kinds of neat exploration. You can also draw a bounding box around any terrain that you want. And if you have a 3D printer, you can generate print files for your 3D printer. This is really popular. These disappear off my desk very quickly. Another really fun thing you can do is you can draw a path anywhere you want with your mouse across the surface. And then the portal will return to you a QR code. Scan the QR code into your smartphone, put your smartphone in a pair of cheap Google Cardboard goggles, and whatever path you drew, you will now fly in virtual reality. So that's kind of fun too. So one of the best things though is to put Moontrek into the interactive 3D mode and go flying. Just using your mouse and keyboard game control keys, you can fly across the surface and go roving around. This is really fun. So, as we look at the moon, we see there are really two main types of terrain. There's the dark, smooth, lowland terrain, and these are vast plains of lava. And then you have the higher, rougher, more ancient, light-colored highlands. Taking a closer look, we can see many of these lowland areas, one of these what we call seas. They're actually vast plains of hardened lava. A lot of them actually fill ancient basins from asteroid impacts on the moon. So you can see here Mare Crisium hole was punched by an asteroid and then it later filled with lava. As we look at craters, we see great diversity among them. The smaller craters tend to be simple pits, rounded bowls. As the crater gets larger, then you start having terraced walls and you have a central peak where you had rebound. Think of like a drop hitting a surface of water. As they get bigger, that central peak turns into a cluster of mountains. And growing larger still, it will turn into a ring of mountains. And in the largest cases, you have multi-ring basins. As we look at craters, the younger craters tend to have these light-colored ejecta blankets around them, sprays of pulverized rock that got blasted out by the impact that formed the crater. A number of craters have actually been filled in by that flooding of lava. So in the case here, we see the crater Plato. It used to have a nice deep interior, but it has been filled in with lava. And in some cases, it gets very extreme. Right in the center there's a crater, Stadius, that is just barely discernible. It's been almost completely overrun by the flood of lava. Looking at another one of the big impact basins here, this is the Iridium Basin, and you can see that mountain ranges on the moon tend to actually be the rims of these big impact sites. So you don't have the same kind of mountain building on the moon that we have here on Earth, but impacts form the mountain ranges. And here we'll use Moontrek to fly along the front of the mountain range there. It's really very cool. This is what the Apollo 15 astronauts saw as they landed right next to that really strange looking feature in the center there that is called Hadley Rill. Let's take a closer look. It almost looks like a dry riverbed, but no water ever flowed here. This was actually carved by flowing lava. And so you can take a close look at this channel, and the astronauts actually drove their rover right up to the edge of it. It's about 3/4 of a mile across, about 1,400, 1,500 feet deep. That's called a sinuous rill. We see other types of rills that are straight rills there, and these are examples here. And this has a different origin. These were actually formed by magma welling up from inside the moon, passing into cracks and wedging the cracks open. And actually, if you look to the left, along the rill there, you'll see a whole series of craters. Those are not impact craters, those are actually volcanic craters. So we see that there are both types of craters on the moon, impact and volcanic. And so here you had magma rising up through these cracks and erupting. Here's another example. You see some beautiful straight rills going there. We're going to change our view. So that's one of the neat things you can do in Moontrek. You can view through many different instruments. So we're changing here to a laser altimetry view to better get a view of topography. And if you look along the left-hand rill there, you can see a line of cinder cones, where again, magma came up through that crack and erupted and formed this line of cinder cones. So that really brings up the whole concept of volcanoes on the moon. And volcanoes on the moon tend to be remarkably unspectacular. They typically have slopes of 1 degree or less. You know, they are very low-lying shield volcanoes, speaking to the fact that the lava that erupted on the moon tends to be very low viscosity, very fluid. Going again to the laser altimetry, we can pick out the detail a little better there. You can see those blister-shaped volcanoes. Here's another great cluster of volcanoes on the moon. You go, oh, yeah, really? But again, with the laser altimetry, there they show up. So again, very low viscosity lava, very thin, runny lava, except for in cases like this. In a few places on the moon, we have tall, steep volcanoes, where the lava that came erupting out was very thick and pasty and built tall, towering mountains. Why was the lava here different? We have no idea. We do not know. But that's why, in one of our upcoming robotic missions, scheduled for the next couple of years, we are planning to go here to the Gruithuisen domes. Another volcanic area that intrigues us is this. This is the Aina D caldera. And we believe our understanding of looking at volcanoes on the moon and understanding the thermal nature of the moon, all volcanism stopped a couple billion years ago. Except for then we look at this and we see terrain that appears to be remarkably young. This looks like young, recent volcanism. That doesn't fit with our models at all. We do not understand what's going on here. A lot of people want to go explore this place. As we look across the surface of the moon, now we see all kinds of holes in the ground, holes from craters, but then we also see these pits that seem to open up into vast voids beneath the ground. We believe that these are actually skylights, collapsed roofs into great lava tubes beneath the ground, caverns where fluid lava once flowed. We also see faults on the moon. So here, the straight wall, or rupus recta, and again, we can use the elevation tool within MoonTrek to actually look at how the ground just steps right up there. We have places where you have parallel faults that can create an area where the block between them can drop down. On Earth, we call that a graben, and it forms a faulted valley. And here we'll actually use MoonTrek to fly up the Alpine Valley on the moon. So here we come, you can see the valley coming up. And interestingly, as we fly up, you can see there's actually appears to be a sinuous rill going along the floor there where lava may have once flowed. And you have the walls of the valley on either side. A lot of interesting geology on the moon. Here's another case. Here we're looking at the Taurus Littrow Valley where the Apollo 17 crew landed. This is deeper than the Grand Canyon. It's a spectacular terrain. And you can see a dark line going across. That is actually the Lee-Lincoln Fault Scarp. And a lot of interesting stuff is associated with that. We can see giant landslides that fell down the face of South Massif Mountain and extended for many kilometers out across the valley floor. And looking up at the mountains, we can see tracks of boulders that have rolled down the faces of the mountains. The moon is actually a remarkably active place. There are moonquakes that get up to magnitude 5.5 and last for over 10 minutes. Now, the moon does not have a global magnetic field the way the Earth does. But it does have localized magnetic fields, just in isolated areas. And in those isolated areas, we tend to see features like this we call lunar swirls, where you see these patterns of light and dark that are mixed together in a way that seem to trace out the magnetic field lines. So how exactly do these form? And what is the source of the magnetic field? Again, we don't know. But we have a mission planned to go here to Reiner Gamma to explore this fascinating feature. So speaking of going to the moon, we're doing that. So right now, we are in the midst of the 50th anniversary of the various Apollo missions. 50 years ago, we were in the midst of Apollo. And we are now looking forward to the next generation of human missions to the moon, Artemis. Artemis was Apollo's twin sister in mythology and was also the goddess of the moon. And with the Artemis missions, we'll have a combination of robotic and crewed missions, including we're going to have the first woman to walk on the surface of the moon about time. So the Artemis missions are targeting sending astronauts to the south pole of the moon. And the south pole of the moon is actually located on the rim of this crater here. This is Shackleton Crater, about 21 kilometers across, more than twice as deep as the Grand Canyon. And it is permanently shadowed. The sunlight is coming in horizontally. The sunlight has not shone on the floor of Shackleton Crater in over 1 billion years. And as such, the floor is actually one of the coldest places in our solar system, even colder than the surface of Pluto. And just as there are areas of permanent shadow, there are mountains that stick up that get almost constant sunlight. That's very useful. That could be a source of power, solar power, right next to these very fascinating dark shadowed areas. And here you can see another place that we're planning to go. This is a mountain right near the South Pole. This is Leibniz Beta. And you may have heard about the Viper rover being run out of NASA Ames just up the road here. And this is going to be a rover that is going to be prospecting for water ice at the South Pole. And it's going to do that on the flat summit there of Leibniz Beta. So if we take a look at the South Pole, looking down, we can see that there are these big, deep, dark, permanent shadows. We can pierce those shadows, again, with laser altimetry. But the thing that fascinates us is, again, in these permanently shadowed areas, we have found that in a number of places, there are large deposits of water ice, which could be a huge resource for us. If you're going to live and work on the moon, ice is more than worth its weight in gold. And it's water to drink, but it's also, you can break it apart to hydrogen and oxygen, oxygen to breathe. You'll really want to do that if you're living, working on the moon. And having hydrogen and oxygen, you have fuel. It's all kinds of good. So moving on then to Mars. We have a portal from Mars. As we look at Mars, we see Mars is a complete and total desert today. No sign of water at all. But if we switch again to a laser altimetry view and we color code it so that blue is low, green is high, or higher, yellow higher still, orange getting higher, we get a different view of Mars. We see Mars's ancient history revealed to us and how Mars was once a wet world. We can see ancient river channels and how they actually flowed into a bay that then opened up into a great northern ocean on Mars. Mars was once a wet world like Earth. We can see in these river channels how the flow of water carved and streamlined the terrain. Mars also has a Grand Canyon, Valles Marineris. And when I say grand, I mean really grand. If Valles Marineris were placed here on Earth, it would stretch from Los Angeles to New York. This is a Grand Canyon indeed, with titanic landslides. And like the Earth's Grand Canyon, it's actually a network of canyons. Here we'll use the Mars Trek portal to fly in to the canyon over sand dunes, and then over the floor of the canyon covered with sedimentary deposits from when lakes long ago once occupied the floor of the canyon. This kind of flying is really fun to do. Mars has volcanoes. Big capital letters, volcanoes. A bunch of them, and they're really big. This is Olympus Mons. Now, a lot of you may have seen in person, or at least pictures, of Mount Rainier, one of our great volcanoes here in the US, towering above the state of Washington. But if you look at Mount Rainier on a map of Washington, it is but a tiny dot on the map of that state. If you were to put Olympus Mons on that same map, it would cover essentially the entirety of the state of Washington. About 3 times as tall as Mount Everest. This is a big mountain. Our biggest volcanoes here on Earth are in the Hawaiian island chain. Maybe some of you are familiar with them, have visited. This is the volcanic caldera on Olympus Mons. You could fit the entire island of Oahu inside there. This is big stuff. And again, it is a broad shield volcano, low slope. Speaking of low viscosity fluid lava erupting over time. As we look at the surface of Mars, we see skylights, pits, just like we saw on the moon. But we're wondering if we know that there's no water on the surface of Mars today, but could there still be water beneath the surface? And if so, might these be really good places to look? Speaking of water, this is Jezero Crater. It's in the news a lot lately. This is where the Perseverance rover is currently operating. And this crater was once a giant crater lake filled with water. You can see on the left where an inflow channel is coming in. If you look toward the upper left, almost to the top, you can see another inflow channel. And then in the upper right, you can see an outflow channel. So this was once a great lake. And if we look at that western inflow channel, we can see as the water flowed into the lake, it slowed and it dropped its load of sediment, sand and gravel, into a big delta deposit. That material was gathered from the highlands, a broad watershed on Mars, back during a time when Mars was at its wettest, was at its most habitable. So it was gathered from that wide area and concentrated right here in this delta deposit. If you're an astrobiologist, this is just the kind of mud pile you want to play in, and that's why Perseverance is going there.
How long ago?
Pardon?
How long ago?
Oh, it's there right now. Perseverance is...
How long ago?
Oh, how long ago did this happen? We're talking over 3 billion years ago. That's even older than the socks in my sock drawer. So, but as you're using Mars Trek, you can look and you can see the layers of sedimentary deposits in the delta deposit. You can see the breach in the crater wall where the water flowed in, and you can fly up the channel, the river, as it goes up into the surrounding highlands. Now, when we send astronauts to Mars, they're going to need water. There's, of course, water at the polar ice caps. We don't want to send them there, though. The poles are really nasty. It's cold, it's mean, you don't want to go there. But fortunately, Mars is cooperating with us because it turns out there are these two bands of mid-latitude glaciers on Mars. They said there's no liquid water, but Mars has no problem with frozen water. These are debris-covered glaciers. They're covered with rock and dust. We see that here on Earth. It's a great survival technique if you're a glacier to have that insulating layer of stuff protecting you from the sun. But here's a good example of a valley glacier, another valley glacier. If you've been up to Alaska, this should look familiar. You've got medial moraines, flow features. Yep, this is a glacier. And we have even Piedmont glaciers, these big toes of ice sticking out. It's really pretty cool. We have types of glaciers surrounding peaks called lobate debris apron glaciers. And glacial ice oftentimes will fill craters into these concentric crater fill features. As we look along the coast of what was once the shoreline of that great northern ocean, and we start looking inland, we see tales of, well, back when that ocean was there, the solar system was a very violent place. It was much more crowded then, a lot of collisions going on, and asteroids smacking left and right. And imagine an asteroid splashing down into the ocean. What would happen? You would get tsunamis. Not little tsunamis, mega tsunamis. Thousands of feet tall, rushing hundreds, if not thousands of kilometers inland. And we can still today see the scars of the backflow channels where the water that had been pushed in is now retreating and flowing back toward the ocean basin. Mars has faults. Mars has active geology. This is an area of great cracks in the crust called the Cerberus fossae. And our InSight probe that has landed on Mars with a seismometer has actually detected Mars quakes coming from this area, from these areas where the crust is being really torn apart spectacularly. And you can fly up through these great rifts on the surface of Mars and see where active geology is happening right now. It's really very spectacular. And you can even see this. This is an area called the Cerberus fossae mantling unit, or mantling layer. It is it's that kind of weird teardrop-shaped thing in the upper left there, right next to a crater called Zunil. And this Cerberus fossae mantling deposit is actually apparently the youngest volcanic activity that we see on Mars. Now, a lot of the volcanoes we see are billions of years old. This appears to be thousands of years old, which tells us that volcanism could still be going on today. And the fact that it's located right near a relatively young crater makes us wonder, could that crater have somehow influenced the volcanic activity? And what the current hypothesis is we know that this is an area where underground it's rich in ice. There's a thick layer of ice beneath the ground. Small asteroid came in 1 to 2.7 million years ago and slammed into the surface of Mars. And it fractured the surface. Lots of cracks forming throughout. And the thought is perhaps those cracks enabled then magma from deep below to start moving up through the crust. And then when that magma encountered the ice, you had a sudden explosion, what we call a phreatomagmatic explosion, where that ice suddenly flashes into steam and blasts out. And so you get this eruption of steam and then pulverized magma that has turned into tiny little droplets of lava flying up through the air. So this is a pyroclastic. Instead of flows of lava oozing out, you have ash blasting up. And so that's the current hypothesis for what's going on here. Now let's move to the planet Mercury. Again, we have a portal for that. You look at Mercury, looks kind of familiar, looks a lot like the moon. Got craters, multi-ring craters. You've got vast plains of lava. You've got fractures where magma probably rose up from below. And amongst all the impact craters, you can see occasionally some of these irregular shaped crater pits surrounded by ash deposits. Those are volcanic pits there. Those are volcanic pit craters, again, where you had pyroclastic eruptions, where you had eruptions sending volcanic ash out over the surface. Then there's the planet Venus. Venus is our next door neighbor. So it's in the same part of the solar system as us. It is about the same size as the Earth. And so for many years, people thought that Venus was probably Earth's twin, and that conditions on Venus might be very similar. When we look at Venus through a telescope, we don't see the surface. We see Venus is completely covered with clouds. And in the early days, people thought clouds, that means water vapor. Ooh, Venus must be very wet, swampy. People even started envisioning dinosaur-like creatures living in the swamps of Venus. Well, then we took a closer look. And it turns out those clouds are made of sulfuric acid, not water vapor. And the temperature on the surface of Venus is a balmy 900 degrees. It's about like your oven in its self-cleaning mode. Pretty nasty. So we cannot see the surface of Venus through those clouds, but we can use radar to pierce the clouds, and that's what we do in our Venus Trek portal. And we see things like the highest place on Venus, Maxwell Montes, towering 36,000 feet. It's that very light-colored area there, and we think it's light-colored because it seems to be covered by metallic snow. That's pretty exotic. Regular snow obviously has no chance on Venus. So if you're going to have snow on Venus, it's got to be, extra heavy-duty snow, metallic. And you have huge volcanic features, like Artemis Corona. I'll get to questions at the end, if I may. So this is, again, this is hardly Earth's twin. But as we look at Venus more closely, we realize that at one point it probably was like the Earth. It did have an ocean of liquid water. But something happened, something went wrong. And actually in studying Venus, that's how we learned about the greenhouse effect, about runaway carbon dioxide. This is not a theory. It exists. It's real. We've got the example right next door. Now, let's move outward between the orbits of Mars and Jupiter, and we get to our nearest dwarf planet, Ceres, which was visited by the Dawn spacecraft and returned wonderful data to us. Ceres is, again, a dwarf planet. It's a small world. If you compare it to the Earth and the Moon, you can see it's significantly smaller, but it's still a significant world. And as we look at Venus, or as we look at Ceres, we see bright patches like this. And when we first saw these, what in the world is that? Snow, but it's not snow. It turns out these are salt deposits. And if you look at the mantle of Ceres, it's actually, instead of like hot silicate fluid rock like we have here, Ceres's mantle is actually an icy slush of salt water. And volcanism on Ceres is water-based. Instead of lava, you have water performing that role. So imagine salt water erupting here. The water then steams off into space, leaving the salt deposits behind. We even have a towering ice volcano, Ahuna Mons, on Ceres. The asteroids are wonderful subjects for study. This is the asteroid Vesta. This is one of the largest asteroids. If you look at it, well, Vesta is large enough that gravity should have pulled it into a nice, perfect sphere. This is not a nice, perfect sphere, is it? The top of it looks pretty good, but the bottom of it, not so much. It's like part of it is missing. Now, the size of everything we're looking at, if you compare Vesta to the Earth, it's, I'd say, one of the bigger asteroids. It's small compared to the Earth, but it's still quite significant. And if we look at the south pole of Vesta, we see why it has such a strange shape. There's a giant impact basin, the Rhea Silvia impact basin, where a smaller asteroid crashed into Vesta about 1 billion years ago and almost destroyed the world and created this big hole. And if you look carefully, you can see the Rhea Silvia impact basin, but look to the upper left, you can see there's another older basin about the same size, Venenia, 2 billion years ago. So Vesta took 2 near fatal hits, blasting away much of the southern part of that world, giving it its strange shape today. And like craters we looked at on the moon, Rhea Silvia has a central peak. This is the central peak of Rhea Silvia crater, and even though Vesta is a tiny little world, that central peak is one of the tallest mountains in the solar system. It rivals Olympus Mons in height. And if we look around the circumference of Vesta, we see these giant grooves indicating how Vesta was almost fractured into tiny pieces. These grooves are concentric around the Rhea Silvia basin. Vesta almost disappeared. Closer to us, here's a smaller asteroid. This is the asteroid Bennu. Bennu is of particular interest because its orbit actually crosses the Earth's. This is what we call a near-Earth asteroid. This could be hazardous. And we recently sent a spacecraft, OSIRIS-REx, to Bennu. It actually touched down, collected samples, and is now bringing those samples back to Earth as we speak. And using our Bennu Trek portal, well, here you can see the size of Bennu. It's only about 565 meters across. It's the size of a mountain, basically. You wouldn't want to be beneath it if it hit. Using the Bennu Trek portal, we can fly into the actual touchdown site on Bennu where OSIRIS-REx gathered its sample. Here, a site called Nightingale. A very similar looking asteroid, also a threat to us, another near-Earth object, is the asteroid Ryugu. And Ryugu was recently visited by the Japanese spacecraft Hayabusa 2 that also collected samples. Here's an example of, I've placed Ryugu against the skyline of Tokyo. You can see Tokyo's Skytree Tower. Again, it's a big chunk of rock, or a big collection of rock. It's actually a rubble pile. And using the Ryugu Trek portal, you can get the various data that the Hayabusa 2 mission sent back to us. We do not have a portal for Jupiter. Too bad. But Jupiter does not have a solid surface. Instead, it is a gas giant with an atmosphere that's just swirling clouds, changing constantly all the time. So we can't make a long-term map of the surface. But Jupiter does have roughly 80 moons. And these moons are good targets. And the moon that perhaps is of greatest interest to us right now is the moon Europa. Europa is covered with a global ice cap. But our first exploration of Europa has revealed that this ice cap is actually just a crust. And beneath it is an ocean of liquid water with about 2.5 times the volume of all of Earth's oceans combined. Here on Earth, wherever we find liquid water, we find life. We would love to know what might be swimming in the oceans of Europa. We can see in cracks of the crust there, of that ice, we can see where really interesting stains of water coming out, stained with organics, are coming out to the surface. We can see rafts of ice, some of them tilted. I don't know if I've got you can't see there's my cursor. There's a raft here that you can see is tilted up and down, so that tells us that it's probably not a real solid surface beneath, because that's got to be able to sink down into something pliable. So this looks like icebergs, as you approach the poles here on Earth. Saturn is another gas giant. We do not have a portal for Saturn, but Saturn has over 80 moons, and these are wonderful, wonderful things to explore. We have a portal for Saturn's moon, largest moon, Titan. And Titan is unique in the solar system for being the only moon. You can see there, it's big. It's bigger than our moon. In fact, it's like Mercury big. It is unique in our solar system for being the only moon with a thick, dense atmosphere. Actually, thicker than the Earth's. And as we use radar to peer down through the clouds of Titan, we see rivers. We see lakes. But at 179 degrees below zero, these aren't rivers and lakes of liquid water. These are rivers and lakes of ethane and methane. Think of like cooking gas, cooled down to the point where it's a liquid. We see seas of this frigid material with chains of islands. This is a pretty interesting place. We have a mission, Dragonfly, that is scheduled to go, and it'll be essentially it'll fly through the atmosphere of Titan. We're looking forward to that. Our Icy Moon Treks portal gives you views of 7 of Saturn's smaller icy moons. These include Enceladus. And Enceladus is again covered with a global ice cap. But we know beneath that ice cap, there's an ocean of liquid water. We know that because you see those fractures, those tiger-striped fractures there. Looking closely, water is actually erupting out of those as geysers. The Cassini probe actually flew through the erupting geysers of water coming out of Enceladus. Again, if you're going to look for life anywhere else in the solar system, this is one of the places you really want to look. Saturn's moon Dione has clearly seen a lot of interesting geology, a lot of resurfacing, big ice cliffs. This is Saturn's moon Tethys. It clearly had a very bad day. That almost destroyed it. This is the moon Iapetus. And the leading edge, in this case on the left, is much darker than the trailing edge. That leading edge is about the same darkness as coal. But on the other hand, if we look at the moon Rhea, it also has a dark hemisphere, but now it's the trailing edge. What's going on? What's the difference? We don't know. Here is Saturn's moon Mimas with the crater Herschel doing a great imitation of the Death Star. And here is Saturn's moon Phoebe doing a great imitation of a wiffle ball. And this moon is different than all the others. It doesn't appear to be light-colored ice. Instead, this is very dark, very porous. It's in a more distant orbit. It's going the wrong direction. What we think is that this may be a captured Kuiper Belt object, one of those distant, frigid worlds from out beyond Neptune that somehow got jostled in to the inner part of the solar system and captured by Saturn. That makes this a very interesting world. So we've just touched upon some of the wonderful features that you can explore going through the solar system. If you go to trek.nasa.gov on your computer at home, you can explore all of these worlds, and we're adding to them all the time. And you can conduct your own exploration. You don't need to install anything. You just point your browser, preferably Chrome, to this website and go explore with us. Thank you very much. So if I haven't rendered you all unconscious by this point, I'll be happy to try and take some questions. Yes, in the back. You had your hand up early.
You said radar were used to, figure out in case of Venus, I believe.
Right.
But radar has very short range, right? Like how did you manage that?
Oh no, radar does not have very short range. We use radar a lot. We have used radar to look at passing asteroids. We send radar beams out. Now we have much bigger radars than you have in your car right now. We have great big dishes, many, many meters across, sending big, powerful beams out, bouncing off and coming back. But so we are able to use radar over significant distances. In the case of Venus and in the case of Venus, we were doing it from in orbit. In the case of Titan, we did it as we flew by. We were able to get radar imagery. So yeah, we use radar quite a bit. And we use it on the moon. The neat thing about when you're using radar on the moon, you can actually penetrate down beneath the surface and you can see kind of some of the stuff there. And that's how we find that there is ice beneath the surface. That's how we find ice beneath the surface on Mars too. We use the ground penetrating capability of radar. Yes?
So you said that there were tectonic plates. How slowly are those moving?
So not tectonic plates. So the only place that we have seen real plate tectonics is here on Earth. Yeah, we have faults. And these are huge. Actually, Valles Marineris is not a canyon cut by water like our Grand Canyon. It's too big for that. So that is a tectonic canyon. That's a tectonic feature. And what we think is happening, and the reason volcanoes on Mars are so big is because it doesn't have plate tectonics. Here on Earth, you can have a hot spot in the mantle, sending a plume up. A great example is the Hawaiian Islands. And as a plate moves across that plume, that hot spot burns a hole and essentially builds a volcano. But then the plate moves on and you get a new volcano, and the plate moves on, so you get this big string of volcanoes forming an island arc. But in the case of Mars, you don't have the plate tectonics, so that plume is just burning through the same spot, and that's why you get volcanoes of such unusual size, as they would say in the movie. Yeah. Yes? What is the size of the Grand Canyon on Mars?
Yeah.
Well, like I say, it would stretch. It is really big. It would stretch, if you put it here on the United States, it would stretch from where we are here in California to New York, all the way across the United States. The walls of the of Valles Marineris are about 8,000 meters tall. That's like the height of the Himalayas, the tallest mountains on Earth. This is a really grand canyon. Really grand, yes. Far back, yes.
Yeah, on some of the moons you mentioned, like Europa and Enceladus.
Enceladus, yes.
Is the water known to be salt or fresh water?
We believe, we haven't gotten samples to bring back to labs yet, but the indications are that it's salty.
Okay, thank you.
Mm-hmm. Yes. Yes?
Do we know what caused Mars to lose its surface water?
Why did Mars lose its surface water? Yeah, we think we've got a pretty good scenario for that. So Mars was a nice, wet, warmer place. But Mars is a smaller world than the Earth. And because of that, it has less of an insulating layer of rock around it. And so what happened is, over time, Mars radiated out its internal heat, cooling down. And it cooled down to the point that the convecting dynamo that you have, like in the core of the Earth, that forms our magnetic field, that type of thing stopped on Mars. And so any magnetic field that it used to have shut down. And that's important because a magnetic field acts as a force field, and it protects our atmosphere from the solar wind, this wind of hydrogen, high-speed hydrogen coming off the sun. In the case of the Earth, that wind hits our magnetic field and gets blown around the Earth. But when Mars's magnetic field shut down, then that wind was free to just slam into Mars's atmosphere and start blowing it away, start eroding it away. And so as time went on, Mars's atmosphere became thinner and thinner and thinner. And as it became thinner and thinner, it was less of a blanket. And so the temperature on Mars started getting colder and colder and colder. If you're planning to be an astronaut on Mars, the nice temperate places that we're planning to go, typical daytime temperatures are about 70 degrees, below zero. Bring your jacket. Yes?
Do we know whether the moon still has a molten core or it's moon entirely cold?
We believe that there is still some small molten core at the deep down in the moon, but it is small and it is not undergoing convection, so you do not have a global magnetic field anymore on the moon. It probably once had one. The moon was once molten altogether. There was a magma ocean covering the entire moon. That goes back to the way the moon formed. The moon and Earth formed together about 4.6 billion years ago in a giant collision when a world about the size of the Earth and a world about the size of Mars decided to occupy the same place at the same time with predictably messy results. And the dense iron cores of both of those worlds sunk together and formed the big dense iron core that we have here on Earth today. And some of the outer silicate rock got blasted off into space. Some of it was lost, but a lot of it formed a ring around the early Earth. Earth had a ring around it like Saturn, but instead of ice particles like Saturn's ring, our ring was of hot molten rock. And then that rock started to congeal and it formed the moon. At first it was really, really hot. Not so much anymore. Yes?
Are there other manned missions other than Artemis which are being planned?
Well, certainly we have crewed missions going up all the time into low Earth orbit. So we've got the International Space Station that we're going to. We're planning new space stations. So a lot of crewed missions to low Earth orbit. Definitely planning a lot of activity on the moon. But then we have our eyes, of course, on Mars. And so our whole exploration strategy at NASA, we call it Moon to Mars. And so what we learn by going to the moon is going to enable us to hopefully safely go to Mars with humans. Yeah.
I think this has to be the last question.
Okay, very good.
So one question about, so the Mars earlier had a liquid water, right?
Say again?
The Mars had a liquid water earlier. So the same amount of water is frozen, or this water, what else?
So we don't know just what the water budget of Mars is. Certainly some amount of water has now dissipated out into space, but there's still large quantities of water in the poles of Mars, in those mid-latitude glaciers, in really widespread sheets of ice beneath the surface, and also trapped in minerals. So there are places on Mars, like on the floor of Valles Marineris, where you have mineralogy. You have rocks that are very rich in hydrated minerals. They can be tens of percent water by volume. So, but it's bound into the rocks, into like polyhydrated sulfates. So there is significant water trapped on Mars, just not in liquid form. So thank you all.
It's a fascinating tour that you give us through the solar system, and I've been listening to your talk, and I'm looking around the average age, trying to judge the average age in the room, and most of this has all been done in our lifetimes.
Yeah.
In the past 50 years or so. I mean, yes, the moon, the Apollo missions were in the 60s and 70s, but NASA has shown us so much, it's almost shameful in some way that we're not more familiar, and it's absolutely wonderful to have an expert guide to take us through this. So let's thank Brian once again.
Thank you.